Yes, thanks a lot for the introduction, and also huge thank for inviting me to this job interview. That's my great honor. So today I talk with the title Categorical Symmetry in 1+1 Dimensions. So before starting, let me introduce and also thank my collaborators. And so this talk will be mainly based on this paper, Symmetries and Strings of Adjoint QCD2, put on archive in the last summer. And this was the work with Zohar Komagosky at the Simon Center, and also the two students at Stony Brook. One is Konstantinos Rumpedakis and Sahan Sif-Nashri. So yeah, both the conceptual and technical details were filled by these brilliant students. So it was my great pleasure to mentoring them. Okay, I also want to thank here to other collaborators on the other related works. So, and these are from the older to younger ones. Here I in particular mentioned the younger ones, that these three were students then, that Poshan Sin and Ryuhei Kobayashi and Yasuri was a student then, and Fei Yang was the younger postdoc. So it was also a great pleasure to work with them. Okay. So let's start. The main theme of this talk will be symmetry. And symmetry is the universal organizing principle in physics. It appears in various places in various ways. So in hydrogen atoms, the wave function are classified by the representation of SO3 or SO3, 1, or the magnetization is characterized as a spontaneous symmetry breaking of the symmetry, or the standard model particles are classified by, again, the representations of gauge group, the standard model gauge group. So it appears in various places. And why we care so much about symmetry is because it's powerful. So in my viewpoint, the symmetry is where the exact equality comes from. So in physics, many things are approximate. However, as long as the symmetry is exact, then we have related exact result. Okay, extreme case is when this symmetry is infinite dimensional, or also known as some integrability. In that case, we can basically solve the system completely, but that's not almost not the case, and we cannot solve the system just by symmetry. Though still gives us important information, because it's an exact equality, and in particular goes beyond the perturbation theory. So so the symmetry is precious tool, in particular in the strongly coupled system that we cannot apply the perturbation theory. Okay, so for these reasons, I think the given a system, what we do first is the analysis of the symmetry of the system. Okay, and I'm interested in quantum field theory, and and my work is most of my recent works are about the symmetries in quantum field theory. So symmetry itself is a literally ancient concept, but there are many things to do in this year. And in the last decade, I think there were two important developments in the topic of the symmetry in QFT. One was the quantum anomaly for discrete symmetry. So the quantum anomaly itself has been studied for decades, many decades, though only recently, I think, except for a few exceptions, that the people thought about the anomaly for discrete symmetry. And that gave us, somewhat surprisingly, that gave us new insights on the physics of strongly coupled systems, including condensed matter physics and also the gauge theories. Okay, and I made contributions to that direction. Another development was the generalization of symmetry, and one of such generalization was proposed by this paper and called higher form symmetry. But more recently, there is another generalization is arising, and that is the main topic of this talk, the categorical symmetry. And I believe that this have a potential to become a new paradigm in quantum field theory. Okay, so let me briefly introduce what the categorical symmetry is. I'm going to talk about detail in the later of the talk. So the ordinary symmetry operations form a group, we say, and in particular for a given symmetry operation, there is an inverse operation. Okay, so means that G times G inverse equals to 1. 1 is the trivial operation. Okay, so the categorical symmetry, roughly speaking, is a generalization not requiring this invertibility of the operation. Okay, so and replaced by something called the dualizability. And mathematically, that such a relaxation leads to something called a fusion category. So hence the name categorical symmetry. And of course, the important point is that these fusion category are realized in the physical system 1+1D systems. So that's important point. And so this is in a sense a new concept, and hence it comes with many names. And so early people noticed this concept. I think this paper they called it a topological symmetry, and this Wen and others, and including myself, call them a categorical symmetry. Others call them non-invertible symmetry, but those are all the same concept. And the important property of this categorical symmetry is that it is preserved on RG flow. Okay, so therefore, we can, in that sense, we can use this categorical symmetry in the similar way we do use in the ordinary symmetry in QFT, in the context of renormalization group flow. Okay, so this, and our contribution was to having found this categorical symmetry in some particular categorical symmetry in a gauge theory in 1+1D, that is the massless adjoint QCD. So the gauge group is SUN. The fermions are Majorana 2D Majorana fermion, but in adjoint representation. Okay, so in usual QCD, it's in fundamental, but here I'm taking the fermion to have fundamental and anti-fundamental two indices. Okay, and so the current for this SUN is formed as a fermion bilinear, and this is just a very standard gauge theory Lagrangian. Because the symmetry of this Lagrangian is these discrete symmetries, Z2 charge conjugation and Z2 chiral fermion parity and non-chiral fermion parity. And this is systems studied extensively back in 90s. And one of the main concerns of them was whether this system is in the confined phase or deconfined phase. So this is title of the paper by these authors. Okay, and our claim was that so they claim that it seems to be in the screening phase, but the precise reasoning was kind of mystery, and we claim that this screening is due to the spontaneous symmetry breaking of this generalized categorical symmetry. That's the rough storyline. So that have been an introduction. And so any questions so far?
Actually, what is there? Will you give a more concrete definition of what is this symmetry? And
Yes. Sure.
I mean, I may have read many times what is a category, but for me, it's still, I mean, it enters through an ear and gets out of the other.
Yes. So first, I talk more about this categorical symmetry and how to define it. Then I will talk about our contribution and give some future directions. Okay, so before talking about that fancy thing, I have to talk about the ordinary symmetry. Okay, and in particular that the topological symmetry operator corresponding to an ordinary symmetry. So let's start from the simple U1 symmetry. Okay, so then for U1 symmetry, we can define symmetry operator for each phase alpha by just exponentiating the natal charge. Here, natal charge is, of course, defined by integrating natal current. And here, this sigma is, I take this sigma to be any codimensional surface in space-time. So in the textbook, it's often taken to be the time slice, the time t equals to t0, some time, constant time slice. But it doesn't have to be. It can be any surface in the space-time. Okay, so this is just the definition of symmetry operator for the U1 case. And the crucial property of this symmetry operator, or even the natal charge itself, is that it is topological. So consider some straight codimensional surface, and like some deformation of it, you just make some bump. Okay, then if you consider the difference between them, then the difference is just this some closed surface. Okay? And if you evaluate this natal charge on this closed surface, then by the Gauss law, it's equivalent to integration over this interior of this surface here. And the integrand is, of course, the divergence of J, but divergence of J is 0 because of the conservation law. Okay, so it's topological, it's standard. And the characterization of this topological operator is as follows: that if you have some local operator with charge Q, then and if you consider some surface enclosing that local operator, okay, like this, then you can because this is topological, you can shrink down the surface and towards the local operator, and that defines some new local operator. But that is gives just a phase. This phase, and this phase is nothing but the U1 action of this phase acting on this of the local operator with charge Q. Yeah. So this enclosing the surface, enclosing the local operator with the surface, it realizes the symmetry action on that operator. That is the characterization of this symmetry operator. Okay. Okay, so this is just a U1 case. But for this generalizes to any group, even G is discrete. So when the symmetry group is discrete, there is no natal current. Okay? However, still this U, the symmetry, topological symmetry operator exists for each element, small g, inside your group. Okay, so again, this is some simple example. So think about the zeta symmetry in Ising model. So in say two dimensions, so you have two-dimensional lattice, and on each side you have spin up or down. And there's a coupling and between the neighboring spins. Okay, then there's of course the Z2 symmetry flipping all the spins. Okay, I can define this Z2 symmetry topological line or topological defect by, so first draw some line. Okay, so this is my line operator, and I declare that I flip the sign of the coupling between the spins crossing this line. So these couplings or this coupling are flipped. So that's my definition of this Z2 topological line. Okay. Then this is in fact topological, because if I move this line, so this part to like this, then I can compensate such move by flipping all the sign or all the spins that passed by this topological line. Okay, so I flip this to spins, and this configuration and this configuration gives the same contribution, and we are going to sum up over all the configurations. So so after summing over over the configurations, we get the same correlation function. And of course, if you don't have any local operator inside this loop, then you can just shrink down to nothing, like this. However, if you have some operator, say this sigma is a spin measuring operator, so sigma gives 1 if a spin is up, and sigma gives -1 when spin is down. Okay, then if this topological line encloses this spin operator, then if you shrink down this topological operator, then we get this negative sign. Because this topological line just flips the spin from up to down. Okay, and that's nothing but the zeta action on this local operator. So again this enclosing operation realizes the symmetry action on the local operator. Okay, so this is the topological symmetry operator that exists for any symmetry in the QFT. And so for topological surface or extended operators, there's an important operation called diffusion. That's just that if you have two topological operators, then these are topological, so you can so in particular you can force these two to crush with each other to form the new topological operator, and I denote this new operator by this tensor product symbol. Okay, and for the case of the symmetry operators that I'm talking about, this fusion is just given by the group multiplication. Okay, and in particular, this symmetry operator have inverse because it's a group, so there is its inverse element for any element, and okay, and if you fuse the two operators corresponding to G and G inverse, then you get the G of the identity, which is trivial operator. Trivial operator means that you do nothing. Okay. So in summary, the ordinary symmetry operation is in one-to-one correspondence to codimension 1 invertible topological operator. Okay. Okay. So that's the starting point of the generalization. And so this gentleman got a couple things I did. Dropped this codimension 1 criteria and and called it the p-form symmetry. So their generalization is not demanding the topological operator to be codimension 1, but it can be any codimension. Okay. So when the codimension of the topological operator is p+1, then they call it correspond. There exists a p-form symmetry. Okay. And in particular, when p equals to 1, that's one-form symmetry, is the precise formulation of the so-called center symmetry, that corresponding to the center group of a gauge group. And yeah, and in particular, this one-form symmetry, p equals to 1 case, this codimension 2 topological operator acting on line operators, not the local operator. Okay, and so in general, the p-form symmetry acting on the p-dimensional operator, not the local operator. Okay, and the virtue of this this p-form symmetry was that it enabled us to think about the quantum anomaly for this p-form symmetry. Okay, so it was not clear what is the anomaly for the center symmetry in before this paper, but now it is clear what it is. Okay? And even we can do the classification of quantum anomaly and blah blah. So there was a huge development, and one of the application was also made almost the same set of authors that about the pure Young methods. And I'm also have various contributions. Yeah, but the main focus of the today's talk is yet another generalization, and that's obtained by dropping the other condition, which is this, the invertibility condition. Okay, so today I only talk about the 1+1 dimensions, and there I just this codimension 1 part won't be changed. So I'm going to talk about the line, which is codimension 1 in 2D, but I do not demand the topological operator to have its inverse. Okay. That's called the categorical symmetry, and because these kind of topological operators are described by a type of category. Okay, and the example of such non-invertible line is in the critical Ising CFT. Okay, so essentially found by Faraday back in the 80s. So this is the Ising model. So again, there is a Z2 symmetry and Z2 symmetry operator, which is invertible. But there's an additional thing that implements the Kramers Wannier duality line. And the fusion rule is like that fusion with itself gives the identity operator, however, also gives some additional term. That's the Z2 line. And therefore, and there's no inverse for this Kramers Wannier duality line. Okay. And so therefore, we say that this Kramers Wannier duality line is non-invertible. Okay. So recently there is also by these authors there is a lattice generalization of this Kramers Wannier duality line. So in the work by Faraday, it's continuous and the construction is a kind of abstract. However, here they really defined it by just giving some weights to each line segments. So now there's very concrete definition of this topological line, and yeah. Anyway, this is the example, an example. Okay, so the data of, in general, the data of topological lines in 1+1 dimensional QFT or even lattice system is in many cases, most cases, described by fusion category. That's the name.
May I ask, could you comment a little bit, clarify where this non-invertibility is coming from? Because if I naively think that, as in your example before, you have just performed some operation in some region surrounded by this line, what stops me from performing inverse operation, and why that wouldn't be inverse of this line of this symmetry?
Okay, so yeah, so all the topological line is in a sense there's a dualizability, so there's something very close to inverse operation. However, it's not quite, and so in this particular case, if you consider some the spin measuring operator, the sigma, and also I can draw some sigma and some L sigma here. So, and L sigma itself is the dual. So if you do, so this is like that do the chromosomal duality twice. Okay? However, this is 0. Because if I fuse these chromosomal duality lines first, then this gives the 1 plus the Z2 symmetry line, and 1 plus Z2 symmetry line projects out this sigma. Okay, so there's there's something close to the inverse operation, but it's still there is an operator that is projected out by that operation.
Thanks.
Kantaro, I have another question. So,
Yes.
so you drop the invertibility requirement, but can you drop both of the requirements? Can you consider higher codimension?
Yes.
Non-invertible.
Yeah. So in higher dimensional QFT, that's the most general thing to consider, and so yeah. So that's not very much explored area in this, new field. So yeah, but I directly eventually thinking about it. But in this talk, I don't have a result about it. Okay, so yeah, so the data of the topological lines in 1+1 dimensional QFT is described by fusion category, and Ferrandi found that in the RCFT, in particular diagonal rational complexity theory, for each primary O, there is a topological line LO, and the fusion rule of LO is the same as the fusion rule of the primary. In particular, it's not necessarily invertible. That's the important class of the examples, class of the fusion categories, and so that have been known for decades, of course. But the recent perspective is that we should understand this fusion category as a generalization of symmetry combined with its quantum anomaly. Okay, that's because it shares significant properties with symmetry, and here I call it such fusion symmetry described by fusion category as a categorical symmetry. Okay, and the crucial property and that is important in this talk is that categorical symmetry is preserved on an RG flow. Okay, in other words, the IR physics should admit all the topological operators that UV has. So, okay, and such topological operators do constrain the possible IR physics. Okay. Okay. Great. So this application itself is not by ourselves, but already made in this paper, but our contribution was to find the categorical symmetry in the gauge theory, and also we found an interesting application of the categorical or physics implication from the categorical symmetry. Okay. Okay. So if is there any questions so far? And if not, I'm going to move on to our own work. And bit pushed. Okay, so yeah, as I said, we consider the SU gauge theory with fermions in adjoint representation. This is the Lagrangian, and the question here is whether this system is in the confined phase or deconfined phase. Let me briefly recall what is confinement. Confinement means that if you put additional probe heavy particle, it's not the massless fermion, but additional probe heavy particle, then if it's confined, there is going to be a flux string stretching between the probe quarks, and therefore the quark antiquark pair feels the potential, the linear potential asymptotically, and it can be such Gedanken experiment can be modeled by a Wilson loop. So if I draw this kind of path, then this part is like the creation, and this part is pair annihilation, and so this part and that part is the world line up to the quark and antiquark. Okay, so if there is a flux string, the flux string fills in inside this loop, which means that asymptotically should give some contribution proportional to area. On the other hand, if there's something screening these quarks, then the contribution will be local to this line. Therefore, the asymptotically we should get a perimeter. So that's the area law versus perimeter law, defining the confinement or deconfinement or screening. And in adjoint QCD, the light matter we have is just this adjoint. And so if we take this quark to be in the fundamental, then neither there is nothing to screen the quark. Okay, so the naive expectation is that we get confinement in this theory. However, these papers observe that it's not the case, and it seems that there has to be a screening occurring in this theory. Okay, so let me briefly explain the old papers in modern terms. So in modern term, there is so the Zn center of this gauge group acts trivially on the adjoint representation, and there is a corresponding codimension 2. This is one form of symmetry, so this is there's a codimension 2, which is local in the 2 dimensions operator, and this is topological, so commutes with Hamiltonian, and this is Zn, so u to the n is 1. Okay, and the Wilson line is charged under this one form of symmetry, meaning that if you consider the commutation between u and this Wilson line, you get this phase. Okay, they found a fermion zero mode when you consider this correlation function of this case power of u on the infinite cylinder. Therefore, this if you have u to the k on infinite cylinder, that gives you 0. Okay, when k is not non-zero mod n plus. Okay, so how can we interpret this? So this infinite cylinder, we can regard this part of the infinite cylinder is preparing a ground state here, and we also have the ket of the same ground state here. Okay, so this u to the k has to be 0 matrix element in this particular state, but also this u is a local operator. So so for that reason, it should be diagonalized in a vacuum. So the only way that this becomes 0 is that the state prepared here is a superposition of vacua. And so there has to be at least n vacua, and each vacuum have different possible eigenvalue of u. Otherwise, we cannot get 0. Okay. And so the one conclusion is that there has to be n vacua, at least n vacua. And the other is that if we have such many vacua with different eigenvalue, then this kind of action is consistent, that the Wilson line acting on a vacuum can start from the other vacuum with different eigenvalue under U, and this part is the excited states. Okay, so and if this is the case, then this means that this Wilson loop have a perimeter law, and suggesting the screening. That's their argument. And recently Chairman Jacobs and Tanizaki and Zhao asked that how can this n vacua arises when the symmetry is only this small discrete group. So when any it's equals to 2, that's fine, but any greater than 3, greater than or equal to 3, it's very unnatural to expect this n vacua. And our answer is that this n at least n vacua can be explained by spontaneous symmetry breaking of categorical symmetry. So it's in the sense there is a slight generalization of naturalness in this sense. Okay, so to find the topological lines, we thought about free fermions, and using all the papers we construct the topological operators just like the Wilson line, Wilson loop, but instead integrating J instead of A. And so these authors ensures that if we tune the coefficient and add the precise correction term, then this type of operator can be made topological. And we also could argue that this survives the continuous symmetry gauging. Okay, and so this line operator exists for any representation R of SUN, but not all of them are independent, and different representation can be related with each other. So list all of the independent lines. We did use some techniques coming from the RCFT literature, and we found that there are actually exponentially many independent lines. So this n is the number of colors, and this should be compared to the fact that the group symmetry is constant of the number of colors, but this categorical symmetry gets bigger and bigger when the number of color increases. Okay, and further, because this is defined like a Wilson line, and Wilson line is just this, we can just connect the two, and that's gauge invariant. Okay, and so there's a line changing operator, and this line changing operator existence for line changing operator says that the two, this L and W, have the same U1 one form symmetry charge. So this commutation relation. In particular, and this L is topological. So if we bring some vacuum, then if we consider this action of L sigma on vacuum, okay, then we can show that this is non-zero, and this one have different eigenvalue under U than this 0 one because of this commutation relation. Therefore, these two vacua have to be different with each other. So this topological line sends one vacuum to another vacuum, or to be precise, a superposition of a vacua. Therefore, we can regard this as a spontaneous symmetry breaking of this topological operator. Oh, by the way, this L box is not invertible, so it's not the ordinary symmetry. Okay, and further we can say that it's consistent to think that the Wilson line acting on this vacuum starts from this another vacuum and plus excited state, and that implies the screening. And at very rough term, we can say that screening is due to this line changing operator, and not by the fermion. Okay, and yeah, so more detailed analysis shows that if you assume the system is gapped, then the most of this exponentially many lines has to be broken. So and therefore there has to be exponentially many vacuum. So it's not just n, but there has to be exponentially many vacuum, and that's was already proposed by Kutasov back in 90s, but it's consistent with that observation. Okay, we also thought about turning on the mass, so mass for the adjoint fermions. So if we turn on the mass, then the categorical symmetry is broken. So then there will be a confinement, but the mass is small, then there is a slightly broken categorical symmetry, and we can actually draw some quantity from that. So in particular, if we consider the tension of the bounded states of K strings, so it forms a bound state. So the tension is not just multiplied by K, but instead we found that it should goes like this. So there's some undetermined constant, but the K dependence is like sign, and I think this is the novel result about this system. Okay, so summary is that we considered this adjoint QCD, and adjoint QCD had a non-invertible topological line operators that I'd like to regard them as a generalization of categorical symmetry because it is preserved by RG flow, and following this paradigm, and by studying these topological lines, we could argue that this system should have this exponential many vacua, and also it explains the screening of the system and computed found the sign law for the tension of the K strings when a small value of mass is turned on. Okay, so let me finish by saying some future directions. Okay, so the near-term future direction is to study more about the categorical symmetry in 1+1 dimension QFT, and NF equals to 2, so 2 sets of adjoint fermion is the most naive target. But once there is a multiple flavor, then there will be a categorical symmetry, or we can think about a quiver, and then there will be categorical symmetry. Also, there is some exotic fusion category that is not look like fair in the lines. That there is some kind of exotic thing that's the Hagerup category. And so one question is whether there is a CFT that admits that non-fair in the line fusion category, and we have some work. There's a good work by Wolf, but inconclusive work, and we are following up it with these people. Yeah, and more long-term thing is to think about higher dimensions, and then we need to use the mathematical language becomes the higher category, so it gets fancier and fancier. So the main question is whether there is a categorical symmetry in non-topological QFT. There's one example, but it's not much well explored, so there's many things to consider. And finally, I would like to briefly mention that, if time permits, that in the adjoint QCD, there's this chaotic coupling, just a fermion-chaotic coupling that is protected by categorical symmetry, but not by ordinary symmetry. So this is neutral under any Z2 symmetries we have in Lagrangian. So from the ordinary viewpoint, there's no reason to expect that this operator is protected. So one might expect that if we run the RG flow, this operator would be generated. But that's not the case. In particular, you cannot find non-zero Feynman diagram that generates this operator, and that's because there is a categorical symmetry that protects this operator. So if you don't have this operator in the Lagrangian at the starting point of the flow, then it won't be generated by the RG flow. Okay, so so I'm curious whether this similar phenomena can be found in higher dimensions. And so this may well be just a special thing to 1+1 dimensions, but at this stage I don't know. But if this kind of thing happens in higher dimensions, in particular in our dimensions, 3+1 dimensions, then it's going to be very interesting. Okay, so the slogan for the research, my research in the next decade will be like that to getting non-perturbative result in the strongly coupled systems from the symmetry in defined in the most possible general sense. That's the slogan. Okay, so thank you for your attention.
Thank you. Thank you very much. And now it's time for questions. So please ask. Yeah, Ken.
Thanks, Kantaro. So this category symmetry, does it always have to be discrete, or can you have continuous ones as well? And if so, is there something analogous to Goldstone's theorem for continuous ones?
Great question. And so far, I'm not aware of, well, there is, okay. Yes, it can be continuous. When it's continuous, then it's not described by fusion category. And so already mathematically becomes shaky. Though I think physically there is. And yeah, your question is whether there is a Goldstone theorem. I expect yes. However, I don't have a good example. So,
or even in this case, right? You have some spontaneous breaking of some symmetry, and that.
Yeah. So in this
for
case,
normal symmetries that has some consequences for the excitations, right, at low energies.
Oh yeah. So in this case, yeah, I should have emphasized, but these are in a sense of a discrete categorical symmetry. So the consequence is this. So you have many vacua in the case. So yeah, so if the Gn is broken, then you expect n vacua. And similarly here the many topological lines are broken, and therefore there should be many vacua. So that, yeah, so that was the consequence. Yes, for the, yeah, it's very interesting question of whether there is a continuous symmetry. So yeah, I know the example where the continuous categorical symmetry in 1+1D, but I do not know in the higher dimensions. In 2D, the continuous symmetry cannot be broken. So, and that applies, I think that also applies to categorical symmetry. So yeah, so I do not have a good example right now. But that's very good, interesting question. Thanks.
Thank you. Do we have other questions? So can I ask a very simple one? A very simple example of a structure that doesn't have an inverse is a semigroup, like a contraction semigroup, Euclidean evolution.
Yeah.
But in so this categorical symmetries are different. Right? So what is the difference with, say, a semigroup?
Yeah, so of course this have a semigroup structure. I can bit different, sorry, because there's a plus. It's more like a ring. Yeah, still. So the main point is that it requires some dualizability, and okay, so the dualizability. So it's not just dropping the invertibility, and it is replaced by dualizability. So what is the dualizability? And so the topological line or topological surface operator should come with the orientation, and so there's a notion of dual of the operator defined by just flipping the orientation. So for the Z2 line, Z2 symmetry, the dual is itself, the generator of Z3 symmetry, then the dual is just its inverse. However, for more generally, there's always some, for a given topological line or topological operator, there's always some dual which is similar, close to the inverse, but like, so in the example of, in the example of Ising, like, so in this case, this is non-invertible, and the dual is actually self. So this is the dual of the DOT line, and starts from 1. So it's close to the inverse. However, there's additional term. So that's the dualizability, and the dualizability comes from the physics side. It's obvious that you can, I mean, you have an operator that you can bend, and like if you have some operator, then you can bend and move like this, and that gives you the dual operator. So yeah, so that's why we mathematically need the dualizability axiom. And yeah, so it's not just the dropping the invertibility, but but coming from the natural picture from the physics.
Thank you. Any questions? There's also from students, postdocs, from anyone.
I'm asking, so what happens in the presence of non-trivial topology? Like if you have non-contractible circle, when the symmetry line is given by an integral of some local quantity that you're guaranteed there will be topological line, kind of both topologically trivial and which wraps around the circle. What is the situation for these lines? Could it be that kind of you cannot get something which is topologically non-trivial because in general it's not an integral of some quantity, right? So
yeah, maybe I couldn't get the.
Let's say you have a sphere on a cylinder.
Mm-hmm.
So is it always the case that if you have topological lines which have trivial topology, meaning that they don't wrap around the circle,
Mm-hmm.
that there will be necessarily also lines which wrap around the circle?
Oh, that's okay. So, well, if the topological line, it does not encircle any cycle, so it's just bounce some disk, then you can just shrink down and get some number, C number. But I guess your question is like that you can starting on the cylinder and draw a small circle, and whether you can go this way, right?
Right.
Okay, so in that case, yeah, actually, so unlike the, yeah, it's better to draw some picture. So you have some cylinder and you have some topological line. Okay, so in invertible case, you get you can make this this larger and larger and get something like this configuration. Yes, for invertible case. But in most general case, you can get some this kind of structure. Like there'll be junction with another line. So if you if you make this small disk larger, at some point you have to collide the two. Okay. And that can give non-trivial line. So the most general case that you can deform this object like this, but with additional line insertion. That's the picture.
Okay, thanks.
Thank you. We have other questions.
Hi, Kantaro. I was curious, what is the like the state of the numerics for this gauge theory? Has this sign law been confirmed at small masses, or is there like prospect for that to be?
So I do not aware of. I'm not aware of the numerical result. It will be very interesting to see it, but yeah, I do not know.
And
yeah.
I also have a naive question. So can we apply this to the you have mentioned we can maybe your future directions extend to 3+1 dimension, right? Is it also possible to extend to the QCD in fundamental representation and also for the massive case rather than massless case?
Right. So so as long as it's in 1+1D, then I mean. So for example, if you consider this SU and fundamental representation QCD, but with many flavors, then there is a categorical symmetry. For higher dimensions, I'm not really, I do not know. It's, yeah, my feeling is that still the real world QCD with the, fundamental clocks with mass, then it's unlikely that there is some weird symmetry. Yeah. Yeah. So in higher dimensions, really, I don't know nothing, almost nothing. Yeah. Yeah, but certainly in 1+1D, you can find categorical symmetry in multiple flavor QCD, and yeah. So yeah, my hope is try to find more examples in higher dimensions. That's future direction.
Thank you. So I wanted to ask a question. So in the large N limit, isn't this adjoint QCD soluble?
Yes.
So how does it how this fact agree with having an infinite number of vacua? Because when you send n to infinity, you have 2 to the n.
Yeah, so it's supposed to be solvable, and there are, okay, so there is a famous paper by Gross, Hashimoto, Klebanov, I think the one, this one is doing some numerics and numerics in large N, and so they say that it's consistent with the screening picture, but I'm not sure that how I'm not exactly sure how to read the paper correctly. One thing is that their numerics is not very clear. It's very old paper, so maybe worth redoing the calculation with the current technology. And yeah, so yeah, I do not have clear answer. It should be solvable, yes, and it should be possible to study some excited states, but I haven't seen the explicit result.
Thank you.
Sorry, but why should it be solvable? Because it's not a vector model, right? It's a tensor
yes.
model. So why should it be solvable in Legend limit?
Yeah, sorry. So it's not maybe not analytically, but like right, you're right. I mean, what I mean is in the sense that you can take the light cone. Yeah, I mean, in the sense utilizing you should be it's sorry. Yeah, the correct thing is that we can do the DLCQ,
Right.
and so that's a gross Hashimoto-Kurebanov. And it should be able to get a clear answer. That's
but numerically, because
numerically, yeah. Sorry, not analytically. Sorry.
It's not like Hooft model. It's not.
Yeah, no, I agree. Sorry. Yeah.
Thank you. So, please, you have questions? Well, one question about names. I mean, in the old days, people talked about fusion rules and then fusion ring, and the operations on these line operators, at least in this concrete example, seem based on the OPE. I mean, on really the fusion.
Yes.
Why is your categorical symmetry, well, a category and it's not just a ring? Okay, so what's the additional or missing structure from being just a ring?
So okay, so why this should be category? So yeah, I think Moore-Zyberg paper essentially captures all the necessary thing. However, it's not just written in the language category. Here, so including the F symbol. So yes. So why we need fusion category? That's one way to say why need the categorification is like for this topological line, then there is a defect operator that living at the end of the topological line, or you can do the state operator correspondence, and it corresponds to the state on the S1, but time-like topological line is inserted. So that's like a defect in going in time direction. And so then there is there is a vector space or Hilbert space for each lines, and that leads to some category structure that in general. Yeah. So in other words, the category, another way of saying it is, and it is in this language, some line changing operator between the topological lines are the morphisms of the category. So that's another way of saying. That's if you have two different topological lines, then there can be some topological line changing operator, and that's thing. So that's why DX3 we need the DX reason that we need the category structure.
Thank you. We have let me ask a question that maybe a little bit more concrete. But here you had a QFT, but you mentioned that some of these methods have been applied to, or could be applied to condensed matter. So have you studied, or would you be interested in studying, say, lattice models? Or,
Oh,
on dense matter models.
yes. So yeah. So as I said, these nice papers and also the more earlier paper by Golden Chain. This paper and directly related. I mean, these models have this categorical symmetry on lattice, and so I'm very interested in this direction. And actually, so I mentioned one future direction here. So this, yeah, a bit esoteric project, but there is some fancy Hagelp category that is not fair in the line, but so according to this Arsen Fendrimon paper, there is a lattice model or like quantum spin chain like model that admits the category symmetry for any given fusion category. That there is a way to construct the spin chain for the given symmetry. And so at least we do have the lattice model that with this very exotic categorical symmetry. So here what we are doing is just trying to find what the Wolf is a PhD was did is try to find a critical point and in the lattice model, and if there is a relativistic critical point, it gives us a CFT with a Hagelp category and symmetry, and such CFT is not known. So it potentially gives us a new CFT, and that's might be interesting. So that's an ongoing subject. Thanks for asking.
Thank you. Please, I don't see any questions in the participant list, so you can voice them, of course. You can ask if you have any. If not, let's thank Kantaro again. And I know that he has also some meetings after that. So thank you very much.
And thank you for all, for that, your attention. Thank you.